Have you ever wondered what separates a simple calculator from the entire digital universe you see on your screen? From the games you play, the websites you browse, to the very operating system running on your device. It's not 1,000 different complex ideas. It's one. A single, ridiculously simple concept that, once you grasp it, unlocks the very essence of what it means to program. That concept is the loop, and more specifically, its most famous incarnation, the for loop. In the dawn of computing, machines were incredibly literal. They were giants that followed a strict one-way list of instructions. Punch card after punch card, they'd execute one command, then the next, and then stop. If you wanted to do something 10 times, you had to write the instruction 10 times. 100 times? You'd need 100 punch cards. It was inefficient, rigid, and incredibly limiting. Programmers quickly realized this wasn't sustainable. They needed a way to tell the machine, do this thing, but do it over and over again until I tell you to stop. This wasn't just a need for convenience, it was a fundamental necessity for creating anything complex. From this need, the loop was born. So, the central question we're exploring today is this: how can such a simple idea, the idea of repetition, hold the power to build our entire digital world? Let's break down the magic. The logic behind a for loop is beautifully elegant and mirrors the way we think every day. It has three core parts: initialization, condition, and iteration. Think of it like this. Initialization is where you start. I'm going to start counting from 1. It sets the stage. The condition is the rule that keeps you going. I'll keep counting as long as the number is less than or equal to 10. This is the gatekeeper. It checks if you should continue or stop. Finally, iteration is how you move forward. After each count, I'll add 1 to my number. This is the step you take to progress. Start, check, repeat, stop. It's a universal pattern. It's how a flower blooms, petal by petal. It's how you build a wall, brick by brick. It's how a musician practices a scale, note by note. The for loop didn't invent this pattern. It simply gave us a language to express this fundamental process of methodical progression to a machine. It encodes a pattern of reasoning that is so natural to us, we barely even notice it. By giving this pattern to a computer, we gave it the ability to perform tasks with a persistence and speed we could never achieve on our own. So, where do we see this in action? Literally, everywhere. The for loop is the unsung hero, the tireless workhorse behind almost every piece of software you've ever used. Think about sorting a list of contacts alphabetically. How does the computer do it? It loops through the list, comparing one name to the next, swapping them if they're in the wrong order, and it keeps doing this, looping, until every single name is perfectly sorted. That's a for loop. When you watch a movie or play a video game, the stunning graphics you see are rendered frame by frame. Your computer is in a massive loop, calculating the position, color, and lighting of millions of pixels, over and over again, 60 times a second. That's a for loop. Machine learning? An AI model learns by processing thousands, sometimes billions, of data points. It adjusts its internal parameters in a gigantic loop, getting a little bit smarter with each pass. That's a for loop. From the encryption that protects your passwords to the core scheduler in your operating system that decides which program gets to run next, it's all built on this principle. Complexity doesn't come from complex instructions. True digital complexity emerges from the rapid and precise repetition of simple ones. The for loop is the engine that drives that repetition. This brings us to a deeper, more philosophical idea. What a computer truly excels at is automating repetition. It never gets tired, it never gets bored, and it never makes a mistake doing the same thing a billion times. The for loop is our primary tool for commanding that power. It's a form of mechanical thinking. We, the programmers, define the logic, the what to do, and when to stop. The machine then takes over the mind-numbing labor of execution. In a way, you could argue that the loop is the closest a classical computer has ever come to having a thought. It's not a creative or conscious thought, of course, but it's a sustained, goal-oriented process. It has a starting point, a purpose, the condition, and a method of progression. It's a sliver of autonomous logic, a ghost of intention we embed into the silicon. When we write a loop, we are bottling a piece of our own reasoning and handing it off to a machine to execute at an inhuman scale. It's a profound partnership between human intellect and mechanical endurance. Now you might be thinking, this is all well and good for old-school programming, but what about the future? Aren't we moving beyond simple loops? It's a great question. Modern programming has indeed evolved. We have powerful abstractions like map, filter, and reduce in functional programming. When you use a map function to apply a change to every item in a list, it looks clean and declarative. But guess what's happening under the hood? A loop. These modern functions are just elegant wrappers, sophisticated abstractions built on the very same foundational looping concepts. They hide the raw mechanics, but the engine of repetition is still there, chugging away. Even the most advanced neural networks, the brains behind today's AI, are trained using a process called backpropagation, which is, at its heart, a series of nested loops that refine the network's weights over countless epochs or cycles. The future isn't about replacing the loop, it's about building more powerful and expressive ideas on top of it. The loop is the bedrock. So, the next time you write a simple for loop, or even use a function that does the looping for you, take a moment to appreciate it. You're not just writing a few lines of code. You are tapping into the fundamental principle of digital creation. You are wielding the very tool that turns simple instructions into sprawling digital universes. To understand the for loop is to understand the DNA of programming. It's the simple, repeating heartbeat that gives life to all software.